Okay, let's begin. My name is Chuanfu Fu from Department of Computer Science and Technology, Tsinghua University. Today, I'm honored to introduce our new research article about machine learning-based malicious traffic detection. We address the issues of robustness and scalability for the emerging security paradigm by analyzing the frequency domain features of traffic. Nowadays, numerous applications dominate almost every aspect of our daily life. These applications generate volumes of traffic, the packet sequences carrying the data of users. A concrete technique behind the Internet is routing and forwarding infrastructure, which constitutes the backbone network and delivers terabit scale information generated by the applications from data centers to our workstations and laptops. Unfortunately, network attacks always emerge. Attacker groups generate malicious traffic, utilize the forwarding infrastructure, and finally jeopardize user security. If we can identify and throttle the malicious traffic on the forwarding path on the backbone network, then we can protect many legitimate Internet users. A potential solution is the traditional signature-based network intrusion detection system. However, the massive fixed rules incur high overhead and cannot identify unknown attacks, zero-day attacks, which have not been disclosed and analyzed. Recently, several practical evading strategies were disclosed. Decades years ago, researchers attempted to leverage artificial intelligence, machine learning, to automatically identify and throttle the malicious traffic in backbone networks. However, it is non-trivial to identify malicious traffic in backbone networks because terabit scale benign traffic with complex patterns is a natural shelter for malicious traffic. Pinpointing malicious packets is nothing but find a needle in a haystack. Traffic feature extraction is a critical step in machine learning-based malicious traffic detection. It transforms binary Internet packets to numeric features used as input for machine learning. From a high level, two types of feature extraction method exist: packet-based and flow-based. Packet-based features are extracted for each packet. However, the large scale of the features poses high overheads for machine learning to process. Thus, they cannot detect threats in real time. As for flow-based methods, they extract cross-grain statistical features for each flow, for each sequence of packet, which incur low accuracy and is not robust to several detection evading strategies, such as injecting benign traffic into the malicious traffic. Thus, real-time and robust malicious traffic detection is still unavailable. Whether we can reduce the scale of traffic features while preserving the fine-grained packet sequential information to better trade off between the detection overhead and accuracy. Beyond the traditional flow-based and packet-based features, traffic features with low overhead, low redundancy, and high effectiveness are desired for real-time and robust detection. We observed Internet traffic has significant frequency domain features, especially malicious traffic, which can represent the sequential information concisely. In this work, we present a real-time, robust malicious traffic detection solution, Whisper. Whisper extracts the frequency domain features, which can represent low-level packet ordering and ensure detection robustness. Meanwhile, the frequency domain features have low redundancy, thus reduce the processing overhead. The efficient, well-concise features make it practical to leverage lightweight machine learning to learn the complex patterns of traffic in high-speed networks. Here is an overview of our method. After arrival of Internet packets, the packet parsing engine of Whisper extracts the raw features from packet sequences, such as packet length and packet type. Then, Whisper performs feature encoding to reduce the scale of raw features. We acquire the encoding vector by estimating the solution of an optimization problem using an SMT solver offline. Next, discrete Fourier transformation is performed for feature enhancement, which also provides invariant representation. The frequency domain feature is more effective than the traditional time series per packet features because burst transformation, and periodic communications are common on the internet. Next, logarithmic transformation provides numeric stability. This moment, Whisper has acquired efficient frequency domain features with low redundancy. Whisper adopts an unsupervised statistical clustering to learn the features with low overhead, which is practical to be deployed in high-speed networks. Now, Whisper completes the procedure of detection. A traffic features theoretical analysis framework based on information theory is proposed, named the traffic differential entropy model. We proved the efficiency of Whisper's frequency domain features, the basis of robustness. The theoretical analysis framework has three core ideas. First, we model the sequence of raw packet features as discrete time Gaussian process. Second, we use differential entropy of the stochastic process as the metric of information. Third, we model the feature extraction as algebra operations on the status random variables. Three insightful conclusions are acquired by analyzing the traditional flow level features, packet level features, and the frequency domain features used in Whisper. First, traditional flow-based features have more information loss during calculating the flow level statistics, such as flow byte count and flow compilation time. Because the statistics cannot represent low-level packet ordering information, they are not robust to evasion attacks and incur inaccurate detection. The conclusion 1 is consistent with intuition and the real-world experiment. Secondly, we prove Whisper can reduce the information loss in flow-based features, which lays the foundations of Whisper's robustness detection. Third, Whisper can also reduce the information loss in packet-based features. However, comparing with the packet-based features, Whisper reduces the feature scale significantly. That is why Whisper achieves low detection latency and high throughput. In conclusion, the frequency domain features in Whisper is a better trade-off between information loss and traffic feature redundancy. The cross-grain flow level features have low redundancy and high information loss, which incurs inaccurate detection. The fine-grained packet-based features have low information loss, but redundancy of features make it infeasible to be deployed. Our experiment verified theoretical analysis result and showed that Whisper works as advertised. A high-speed network testbed, we replay kinds of malicious traffic, including stealthy attacks, complex multi-step attacks, and evasion attacks. To simulate real-world deployment, we replay backbone network traffic dataset in high speed as background traffic for 5 to 15 gigabit per second. Here is a summary of the experiments. First, Whisper has at most 18% accuracy improvement than the state-of-the-art method. From the scatter diagram, it is obvious that malicious and benign traffic can be clearly distinguished via frequency domain. To evaluate the detection robustness, we assume the attacker can inject packets generated by various benign applications into the malicious traffic. It is common in recent discovered botnets. We observed that the evading method decreased the accuracy of baselines for at most 13%. But even attackers inject high ratios of benign traffic, Whisper can still maintain accuracy around 90%. We also measured the throughput of Whisper. Whisper achieved 13 gigabit per second throughput. Off-the-shelf commercial server, which is also 2 orders of magnitude improvement than the state-of-the-art packet-based methods. We measured end-to-end detection latency and concluded that Whisper reduced detection latency to 10 millisecond scale. In summary, to achieve real-time and robust detection, Whisper used the frequency domain features of traffic and leveraged lightweight machine learning. The 3 core components of feature extraction are feature encoding, Fourier transformation, logarithmic transformation, which produce efficient traffic feature with low feature scale. Lightweight statistical machine learning is used to achieve real-time and robust detection in high-speed network. A traffic feature theoretical analysis framework based on information theory is proposed to prove the effectiveness of Whisper's frequency domain features. Physical testbed experiments show that Whisper achieves 13 gigabit per second throughput with high accuracy on various attacks. This is our recent work Whisper, a real-time and robust malicious traffic detection method based on the frequency domain features of traffic and lightweight machine learning. That's all, thank you.